Hello everyone, welcome back to the F equals MA Club, day 8. This is going to be the online lecture for our 8th lecture for the F equals MA Club, and today we're going to be talking about oscillations and waves. And just a little bit of a preface beforehand, oscillations and waves isn't going to be tested much. Over the 15 years, remember that means 15 tests and 25 questions each test. There have only been 18 questions about oscillations and waves, compared to gravitation, which is also very minimally tested, which has 19 questions. Compare this to topics like kinematics and dynamics, which are going up to like 70s and 80s, and you realize that oscillations and waves aren't going to be too important of a topic. But it's just nice to know, and yeah, let's get straight into it. So before we get started, just a little bit of a review. Last time we talked about gravitation, we talked about Newton's laws of universal gravitation, and we talked about Kepler's laws. We talked about gravitational force and its equation, and we also talked about the constant. We talked about gravitational potential energy and acceleration and velocities. And we also talked about Kepler's 3 laws, which are listed below. We also talked about some extra stuff such as shell theorem and vis-viva equations. But if you really do want to learn more about this stuff, go check out the original video, and if you want to learn more, search it up on Google. Remember, I'm not a qualified teacher, so it's just nice to consult a source that's much more reliable than me. Without further ado, let's get straight into oscillations. So first we talked about simple harmonic motion. So this is a type of periodic motion. This is its formal definition, by the way. It's a form of periodic motion where the returning force is always directly opposite to the displacement. And so we can see this in the typical example of a block attached to a spring, where over time it's going to have this kind of sine wave looking graph by position and time. And so this is proved by using Hooke's law, with F equals negative kx, and given for a spring mass system, we know that our d squared x over dc squared, so basically second derivative of our position with respect to time, is going to give us negative kx over m. And so the solution to this is going to be this equation, where our angular velocity is going to be our equal to the square root of k over m. And so in general, if our acceleration, which is what this is, if our acceleration is going to be equal to negative something times x, then it's going to equal to this for our position, or our angular velocity is going to be equal to the square root of this something. And so if we have a constant, that means that we're going to have this initial position added, but our angular velocity is also going to stay as something. And so this is going to come up a bit more important later on. But so what's important about this is we have this equation, right, where we have this negative something times x. And so what we can say, this is our acceleration. Our second derivative of our position with respect to time, that's our acceleration. So we can say that our a is going to be equal to negative something times x. And so we can just say that this something is going to be equal to a over x, right? And so how this is important is that this something is going to be, it's formally defined as omega squared, excuse me. So we can actually bring this straight into our period equation, which was shown there, which is 2 pi, and remember that this flips, so this is x over a, right? And so this is going to be really important later on. But yeah. So moving on, let's go back here and move to the next part. So we have these motion equations, and these aren't actually tested on the F equals MA exam too much. The original sources that I came from, these equations were used for a 2012 problem on the F equals MA exam. I'm pretty sure there were like 2 problems or 3 problems that had to deal with these equations, but you typically won't see them anymore. It's just nice to remember them. So displacement, velocity, and acceleration. And we have our maximum values. So our maximum position, velocity, and acceleration are shown here. And this is just a nice diagram to go to. Next, we have energy. So the potential energy of a spring, we know that that's our elastic potential energy, which is 1 over 2 times kx squared. So the total energy of a simple harmonic motion system is going to follow these equations. These look really hard, but mainly how you're going to see them is going to be 1 over 2 ka squared is going to be equal to 1 over 2 mv squared plus 1 over 2 kx squared. And so this is going to be our maximum amplitude. So that's basically going to be the farthest that the block reaches away from the origin, right? Or the equilibrium point. So this is a displacement at some point in time. This is going to be your kinetic potential and your total mechanical energy, right? So let's say we're here. We have this x. This is going to be our total A or something like that. And so, yeah, that's basically how that part works. And you're going to see that a little bit more than those god-awful equations. But next we can move into periods. So periodic motion is a motion that repeats itself. So something like an orbit where we have maybe some planet orbiting a star, it'll at some point return to its original position and continue to repeat itself. So simple harmonic motion is a very special form of periodic motion, since its restoring force is always going to be opposite of its displacement. So as we can see with the spring kind of thing, we could tell that our restoring force is always going to be pointing the opposite direction of whatever direction it's moving in. So this is very different from other forms of periodic motion, such as the circular motion. This restoring force is not always going to be pointing opposite of displacement. In fact, I don't think it will. And so we have that our frequency, these are just a few equations that are nice to know. Our frequency is actually going to be the reciprocal of our period, which is denoted as this big T. We know that our omega, our angular velocity, is going to be 2 pi times our frequency, which is also going to be 2 pi divided by our time. And so that means that our time is going to be 2 pi times the square root of m over k. And we have, for a spring mass system, and for a pendulum with a small angle, we have 2 pi times the square root of the length of the pendulum divided by our gravitational acceleration. So for a pendulum, you actually don't need mass. But remember this small angle thing. Large angle pendulums, there's been one question that I've seen throughout the entirety of F equals ma, so I don't think that's going to be likely to pop up. But for larger angles, this equation isn't going to work. If you've try your best, it's not going to work. But yeah. Next, we have multiple springs. So there's two types. We have springs in parallel and springs in series. For springs in parallel, it's going to look something like this, where our spring constants, which are these k's, they're just going to add together. And for springs in series, so something like this, it's actually going to be something like a reciprocal equation, which is going to be weird. So let's say our first spring constant has like a spring constant of 10, then like 5 or something like that. That's going to be 1 over 10 plus 1 over 5. It's going to be 1 divided by our total spring constant, right? That's going to be 3 over 10. So our spring constant is actually going to be 10 over 3. So next we have waves. Waves aren't going to be a big thing. Out of every single F equals ma test that's ever been had, there have only been 3 problems about waves. And so this isn't going to be too big of an explanation. So waves are traveling oscillations. Energy is propagated, but the object itself is not. If you ever have a wave equation, this is not important. These two things, where our omega is going to be 2 pi over t, and this k, this is not a spring constant, is going to be equal to 2 pi divided by this lambda. And this lambda is our wavelength. So these equations are a bit more useful. We have the speed of waves is going to be equal to our wavelength times our frequency. Our tensile strength is actually going to be this tensile strength coefficient times our cross-sectional area. And we have that the speed of a transverse wave is going to follow this equation, right? So it's our tension force divided by this mu. And we can actually simplify that into this, where it's going to be the square root of our tension force times our length divided by our mass, right? I think that's about it. So let's move straight into our worksheet. So first problem. A block of mass 3 kilograms is moving on a horizontal surface towards a massless spring with a spring constant of 80 newtons per meter. Coefficient of kinetic friction is 0.5. Block has a speed of 2 meters when it first comes in contact with the spring. How far will the spring be compressed? So this is not a hard question. This is just a conservation of energy thing, so we can write that our potential energy plus our kinetic energy is going to be equal to our final potential energy plus our final kinetic energy plus non-conservative work, which is actually going to be useful because we have friction. We can say that at the start we have no potential energy. At the end we have no kinetic energy, and yeah, we can just go from here. We have 1 over 2 mv squared equals 1 over 2 kx squared. Remember, potential energy of potential elastic energy. And our non-conservative work, a lot of people actually tripped up on this. Remember that our work is going to be equal to a force times distance. Our force is going to be our frictional force, so we can denote this as mu. Our normal force is mgx, right? So that means that our equation is going to look something like this, right? I'm just going to erase this stuff for now and change the brush, hopefully back. And so let's just plug in some values. This is going to equal to 6. This is equal to 40x squared. And this, I think, is equal to 15x. Let's just move this 6 to the other side. So we have 40x squared plus 15x minus 6 equals 0, right? You can plug this in, you can hand do it, but you're finally going to get x equals negative 0.61 and x equals 0.24. We can't have a negative distance. That would mean that the spring, after being compressed, suddenly shoots outward. Like once the object touches the spring just like says no you and then expands. So that's not going to work. So our final answer is going to be 0.24 meters. And if we look back on our slideshow, not our slideshow, our worksheet, we're going to see that that's going to give us the value of an answer of B, which is 0.24 meters right here. Next, a mass hangs from the ceiling of a box by an ideal spring. With the box held fixed, the mass is given an initial velocity and oscillates purely vertical motion. When the box reaches the lowest point of the motion, the box is released and allowed to fall to an observer inside the box, with the falling quantities does not change when the box is released. So the big thing that we need to know, period, the period is not actually affected by the acceleration of the system. So the period is not affected by the acceleration of the system. This is really important, and we can actually look at the equation and actually look at it and use our brains and realize that the period for the spring mass system is just not going to be affected by the acceleration. And so if we just go back, that was quick, but we can just see that that's going to be the period of the oscillation, so B. Next, a spring is set up as follows: platform with a weight of 10 newtons is on top of 2 springs, right? Each with spring constant of 75 newton meters, right? All right. And so a third spring on top, right, also with a spring constant of 75 newtons, and a ball with a weight of 5 newtons is placed on top of this system, and it's asking for how much the height changes for the spring system. So what's really important is we don't need to calculate the height change for this object, because it's only asking for the change in the height after we put on the ball. So we can just set the original height as the original height, and then we just have to calculate how much these springs compress after we put down this, right? So let me just move this while I have the time to do so. All right, so we first have these 2 springs in parallel, right? These 2 springs are in parallel. Next, we have basically this this system of a spring plus this spring is going to be in series, right? So let's calculate these individually. Let's first do the parallel ones. So K parallel is equal to K1 plus K2, remember? And so that means that we're just going to have 2 75s, which means our spring constant of these 2 springs in total is going to be 150 newton meters. Next, we have our series. So this equation goes like this, remember? So we're going to have 1 over K1 plus 1 over, I'm just going to say K and just put that parallel symbol. So that means that our spring constant in series is going to be 1 over 75 plus 1 over 50, which means 150, which means that our total spring constant of our system is going to be 1. So 1 over our spring constant is going to be 1 over 50, which means that the spring constant of the entire system is going to be 50 Newton meters, right? And so if we were to zoom this down once again, right, that would mean that our force is equal to negative kx, remember? And so the net force has to be 0 by the time that everything's settled. So we can say that negative kx plus mg, the weight of the ball, is equal to 0. That means that mg equals kx. We don't even need to put g. This is the weight. Remember that this is in newtons, right? So this is 5 equals 50x, right? So x equals 5 divided by 50, which is equal to 0.1 meters, right? And so that's going to be our final answer right here. And if we simply look back on our slideshow, not our slideshow, our homework, we're going to see that that's going to give us C, which is 0.1 meters. Next, an object of mass m is hung on a vertical spring with a spring constant k and set into vertical oscillations. Period of this oscillation is t naught. Spring is then cut in half, and same mass is attached, and the spring is set up to oscillate on a frictionless inclined plane, making an angle theta to the horizontal. Determine the period of oscillations in terms of t naught. All right, so let's give you a little question, right? Given a spring, if you cut the spring in half, what is the spring constant of each of these springs? And so there's a really nice solution to this, which is, let's say that we stretch this original spring by some x, right? So kx, right? Now let's say this x that we stretch by is like 2 meters, right? Now let's say we cut the spring in half and we stretch each of these springs by 1 meter. Like we elongate it. I don't know how to pronounce stuff. We stretch these each by 1 meter. That will produce the same amount of restoring force as just having the spring stretched by 2 meters, right? Because if I apply the same amount of force to stretch each of these by 1 meter, it shouldn't be different, right? If you get what I mean. So that would mean that our kx is equal to k prime x prime, right? We know that our x prime is just going to be 1 over 2 of our original x. So we can say that our k prime times 1 over 2x is equal to kx. Eliminate the x's, k prime is equal to 2k. So each of these spring constants has a spring, the springs has a spring constant of 2k. That means, oh no. That means for our period, we have the equation 2 pi times the square root of m over k, right? This k, for our new tension, it's going to be 2k, right? Which means that t, our new t, is going to be equal to t naught divided by the square root of 2, right? That's the only thing that's different. These aren't different. These aren't different, right? And so we can just say that. That's it. The thing about the inclined plane doesn't matter. The angle doesn't matter. So we're just going to get d, which is t naught divided by the square root of 2. Next, a spring has a length of 1 meter when there's no tension in it. A spring is then stretched between 2 points 10 meters apart. Wave pulse travels between the two endpoints, time of 1 second. Spring is now stretched between the 2 points that are 20 meters apart. New time it takes for a wave pulse to travel is now closest to one of these values. All right. So let's take that original equation into account. So V is equal to our tension force times our length divided by our mass. Our tension force, that's just going to follow by Hooke's law. So we can just say kx. The negative doesn't really matter here. So that means that our velocity is equal to kxl divided by our m. Both of these double, right? For v prime, this becomes 20 meters. This becomes 20 meters, right? Both of these become 20, like 2 times of what they originally were. So that means that v prime is equal to 2v, right? So you might think, oh, so it's e, 2 seconds. No, The thing is, we also stretch the string twice of what the original measurement was. So remember, we have the equation, our time is equal to distance divided by our velocity, right? Which means that 2d divided by 2v. Our time's going to stay the same. If we look back here, that just means that we're just going to see 1 second. Because our time's just not going to change if our distance is doubled and our velocity is doubled. So we're just going to see 1 second. Now for the hard ones. I actually had to do research on this. I don't even know if I can actually prove this properly, but we can just give it a shot. So, a uniform rod of length L lies on a frictionless horizontal surface. One end of the rod is attached to a pivot, an unstretched spring of length L, which is much greater than this length, lies surface perpendicular to the rod. One end of the spring is attached to the movable end of the rod, and the other is attached to a fixed post here. When the rod is slightly rotated about the post, it oscillates. Wow! So, spring attachment is moved to the midpoint of the rod. So, again, set into small oscillations. What is the new frequency? Right? So, this is how we're going to do this, right? We had our original equation, which is, nope, that's the eraser. T is equal to 2 pi times the square root of x over a, right? So that means that we have our acceleration is remember our rotational analog to Newton's second law, which is that our torque is equal to our moment of inertia times our angular acceleration, which is equal to our force times radius, right? And sine theta, remember, sine theta, you can put that here, but since this is perpendicular, we can just eliminate that, right? So, that means that our torque, our force, remember, that's just going to be kx, right? So, kx r equals I AR, right? A divided by r, right? Because that's our angular acceleration. So that means that our angular acceleration is equal to kx r squared divided by I, right? And if we put that back into this period equation, that was a great circle. If we put that back into our period equation, that means that our t equals 2 pi times the square root of xi divided by kxr squared. We can eliminate both of these x's because that's just our displacement, and that just can't be canceled off. So that means that our period is equal to 2 pi times the square root of our moment of inertia over kr squared, which means that this is directly proportional to 1 over r. Right? And next, our frequency is going to be equal to 1 divided by our period, which means that it's directly proportional to r. This is, and so since our r is that's just going to be the length of the rod, right? For our original one. And since it's halved, it's put at the midpoint of the rod, that just means that our frequency is just going to be f over 2. So that's going to give us a, which is f over 2. All right, on to the next question. So, spring attachment is now moved back to the end of the rod. Post is moved so that it is in line with the rod and the pivot, and the spring is unstretched. Post is then moved away from the pivot by an additional amount, L. What is the new frequency of the oscillation? So this is going to use that same equation, right? Where we have t is equal to 2 pi times the square root of x over a. Now, this is going to be kind of interesting. Our a is equal to our, remember IA equals torque, which equals our force times our radius, sine theta. And now theta actually matters because the displacement creates an angle. That's actually important. So this is going to create kx. Remember that this is going to be, our r is just going to be our L, right? Our L, right? And so something really important pops up, right? So we have our f r sine theta times our L, and our displacement here is actually going to be L. So x is going to be equal to L sine of theta. And since these are really small angles from how long this is, we can actually approximate this. This is a small angle approximation, which means that this is now going to be around L theta, right? Because sine theta is around theta for small angles. So we can now say that this is basically just going to give us, and sorry, we have to erase this. I said it in the wrong portion. Sine theta mattered here. And so what we can say is, since this is f sine theta, we can just say that, right? And so that gives us KL theta times L, right? And so, wait, no, I did this in the wrong order. Sorry. And so that means that we can say that this is f sine theta times our L, right? And the thing is that our x is equal to L sine of theta, which is approximately L theta, as said before. And so this means that this is, and remember, we can approximate this as well. So we have KL theta times L, which means that this can just be KXL, right? This makes it really convenient for us because we can just say that our A, remember that A is now equal, A over L is equal to our angular acceleration. This is supposed to be an alpha. I'm very sorry about that error, but that means that our our acceleration is going to be equal to L times our alpha, which means that our acceleration is going to be kxl squared divided by our moment of inertia. So I'm just going to move this aside a little bit. This is quite a hard problem, as you can tell. And now from here, we can do the same thing that we did before. So t equals 2 pi times xi divided by kxl squared, right? So we can cross these out. And so this means that here, yeah, so that means that this is directly proportional to 1 over L, and L doesn't change, right? And so that means that our frequency is also just directly proportional to L, and since it doesn't change, our frequency just stays the same. And if we go back to our worksheet here, that's just going to give us C, which is F. All right, and on that note, that's about to be it. Thank you so much for listening, and I hope you have a great day, and I'll see you next week. Bye.